Good evening, everybody. Hello. 200 at 77. Yes, it sounds a bit cryptic, but what I'm describing is this particular instrument, this scientific instrument. I'm a scientist. I'm interested in science, but this evening's talk is not about science as such. In a sense, it's how I got interested in science, because this instrument, which is a telescope, and telescopes are measured or defined by the size of the mirror that collects the light. And this is a sort of cross-section, if you like, of this telescope. And the mirror at the bottom has a diameter of 200 inches. So this telescope was known as the 200-inch telescope. It is now 77 years old. 200 at 77. And it was dedicated in 1948, hence 77 years old as of now. But I'm going to tell you about how this instrument effectively came to be. So I'm sure you're aware that astronomers find out about the universe by building telescopes that collect light, that allow them to see distant objects, faint objects, hopefully show more detail than can be seen possibly with the naked eye. So my story with this 200-inch telescope starts with this image. The image was taken in 1951. I didn't see it at the time, because at that point I wasn't born. But some years later, I was at school in the library reading an atlas of the universe, or looking at the pictures of an atlas of the universe, and I saw this image. So I'm not sure if I was a teenager. It would have been in the early 70s I first saw this image. And I thought, wow, is that what the universe looks like? Why does the universe prefer to be in the shape of chess pieces? What is this horse head? What's it made of? How did it get there? Why does it look like that? Why is it bright in the top half and dark in the bottom half? I had all sorts of questions that were raised by this one image. So you could argue that this one image alone was responsible for kickstarting my interest in astronomy and hence my interest in science. Because when you look at an image like that, you ask yourselves, if that's what the universe looks like, then what else is out there? So this talk is not about astronomy, it's about the telescope that took this picture. This picture was taken in 1951, and then I thought, right, if a telescope is capable of taking a picture like that, how do you go about building a telescope that can produce images like this? And that has fascinated me ever since. When I was born, and for most of my childhood, this instrument that I'm talking about, the so-called 200-inch telescope, was the largest telescope in the world. And it remained the largest telescope in the world for the best part of half a century. The fact that it wasn't overtaken until some 50 years later is a testament to how fantastic this instrument was. So I'm going to talk about this person, George Ellery Hale. Eventually, the telescope became known as the Hale telescope, but during this talk, I'm simply referring to it as the 200-inch. George Ellery Hale was an astronomer who became a billionaire whisperer. He was very good at talking to people with money, saying, "Give me money to build bigger telescopes." And he actually built the largest telescope in the world, which had a lens 40 inches in diameter, and then he built, after that, the biggest telescope in the world, which was a 60-inch telescope, and after that he built the biggest telescope in the world, which was a 100-inch mirror, changing from lenses to mirrors because that makes life easier for big telescopes. And what I'm talking about this evening is building the 200-inch telescope. How do you go about deciding where you're going to put it? How do you make a mirror that's 200 inches? And for those of you who prefer metric, 200 inches is approximately 17 feet, which is 5 meters. So I'm not sure what that is. It's a little bit less than the width of this lecture theatre, but it is basically huge. How do you go about making a glass mirror 5 meters in diameter? And how do you make it accurately enough to focus light from a galaxy 1 billion light years away? And how do you go about making the telescope? I'll briefly say something about what it's doing now. I've put there 75 years on. Clearly I need to update that because that was written a year or two ago, and I really ought to say 77 years on. And then I'll acknowledge where I've got most of the information for this evening's talk. So this is the man, George Ellery Hale, an astronomer, and it'd be great to tell you about what this astronomer has done, but the talk this evening is about not the astronomy that he did, but his vision and his desire and his ability to get funding to build the largest telescopes in the world. He was actually interested in looking at the structure of the sun, but then realized if he wanted to look at the structure of other stars in our galaxy and in our universe, he would need the biggest telescopes. And rather than try and use other telescopes, he said, I want a larger telescope. No one's got one. I'll go out and build one. That was his philosophy. So this started for him at the tail end of the 1800s. In 1900, he was in charge of the Yerkes Observatory in America, and that housed the largest refracting telescope, meaning a telescope that had a lens at the end, and the lens, although it looks tiny here at the top end, was a full 1 meter in diameter, 40 inches or so. So you can see the size of this telescope. He then, a few years later, obtained funding. I'm not going to give you the full story of how, but then he got some funding to build a 60-inch reflector. So now we're changing to mirrors to collect the light, 60 inches in diameter. And then he built the 100-inch Hooker telescope, so named because an oil magnate called Hooker provided the funding and hence gave his name to that particular telescope. So these became successively the largest telescopes in the world during the first part of the last century. Notice that each big change in the size of a telescope, the size goes up roughly half as much again, from 40-inch to 60-inch, from 60-inch to 100-inch. So you might think, well, the next logical step, if you want to build a bigger telescope, is you start planning 150 inches or thereabouts. But Hale figured, no. Let's go big or go home. Let's not think about 150. Let's double the diameter of the mirror. And that means instead of a collecting area that's with diameter 1.5, that would be twice the area. If you're doubling the diameter, you've got 4 times the area. And with telescopes, especially telescopes looking at faint objects, it's all about the size of the mirror. Yes, size does matter. Yeah, so the larger the mirror, the more light you collect, so the fainter the objects you can see, and the more detail you can see in the objects. That's why throughout the centuries, ever since Galileo pointed his telescope at the skies, there's always been a drive to get larger and larger telescopes, meaning larger and larger mirrors. So moving on from the Hooker telescope in 1918, back in these days, we weren't even sure what the universe was. We knew there were stars out there, but we weren't actually sure that there were lots of galaxies out there. We now know that there are something like 2 trillion galaxies in the observable universe. But 100 or so years ago, we weren't actually sure about that. We knew there were lots of stars in our galaxy, but we weren't actually sure what was beyond our galaxy. We needed telescopes like these to actually answer these questions. As soon as the 100-inch telescope was operational, Hale then said, let's think what happens next. He was always going from one project to another. As soon as he'd got the funding to design and build and get operational a given telescope, he was also thinking, what next? So when the 100-inch was built, he said, we want more light. Astronomers want more light. So let's think about not 150-inch, let's think about 200-inch telescope. In the past, he had approached people like Carnegie to get funding. In this particular case, in 1928, he approached the Rockefeller Foundation and said, please give me enough money to build the world's largest telescope. It is going to be fantastic. Somehow, he managed to get them to commit to not only building a telescope, not only a telescope in a big observatory dome, but the entire infrastructure of the observatory, which didn't exist at the time, was paid for by the Rockefeller Foundation. $6 million at the time. In 1928, that was an awful lot of money. Something like perhaps 600 million now. So basically, you've gone to somebody, said, please fund this project, and they said, yeah, sure, here's $600 million, go make it. And that was effectively what happened. Where are you going to put this telescope? Well, George Ellery Hale was based in Los Angeles, and he had a somewhat parochial view of the world. Now, when we think about where are we going to put telescopes, we try and find the best location in the world in terms of the best clarity of skies, the best so-called seeing conditions, which might be Hawaii, might be the Canary Islands, might be the Atacama Desert. But George Ellery Hale was based in California, and he had this view that all of the world's best astronomers were in Los Angeles. Now, you can argue whether that was correct or not, but he wanted this mega telescope to be close. He didn't want to build a telescope halfway around the world and, as it were, lose control of it. So he wanted something fairly close to Los Angeles. So there's Los Angeles, there's the island of Catalina. Previous telescopes, like the 100-inch, the 60-inch, and not the 40-inch, the 60 and the 100 were built in Mount Wilson, which is this mountain just to the north of Los Angeles. And you can appreciate, as Los Angeles grows as a city, more and more streetlights. I mean, how many streetlights are there in Los Angeles? That would make it very difficult for a telescope positioned here to see a pristine night sky when there's so much light pollution next door. Not only that, but Mount Wilson here is not only polluted by Los Angeles to the south, but then San Fernando, San Bernardino started to become more populated. So in effect, the entire mountain was getting surrounded with light pollution. So they said that mountain is not the best place to put our new telescope. Where are we going to put it? He sent out scouting parties. He didn't want to go too far from Los Angeles, so he sent out scouting parties to look at the mountains to the south of Los Angeles. He also took advice from geologists. He found a few possibilities. His geologist friend said, no, not that one. That one is on the San Andreas Fault. Do not build there. But there is a possibility. You seem to have earmarked this Palomar Mountain. That, my friend, according to geologists, is well worth considering. Palomar Mountain is a slab of granite, 30 miles long, 10 miles wide, 25 miles deep. It is a few trillion tons of granite. If California has an earthquake, that is not going anywhere. So build your telescope on that. Bolt your telescope mounting to that slab of granite, and you will have a nice, steady place to observe from. The only downside is, well, there is this little village called San Diego to the south. Palomar, the scale is down here, but Palomar is about 100 miles from Los Angeles and about perhaps 50 miles from San Diego. San Diego at the time wasn't that big. Yes, it has since grown up, and yes, there is some light pollution from San Diego. But 50 miles is just about far enough that even if you're lighting up the sky with street lights, then 50 miles away, your skies are still reasonably dark. That's what Palomar Mountain looks like. Rather beautiful in the spring, but bear in mind that it is at an elevation. It's the top of a mountain. It's 6,000 feet or so, 1,700 meters. So although it looks rather nice in the spring, bear in mind that, yeah, I was there and I was in shirt sleeves. That was back in 1982. I had slightly longer hair back then. You probably can't tell. That was when I was a student. I visited the Palomar Observatory because I was so impressed with this piece of engineering. But yes, in the spring, it's nice and warm, but bear in mind at that elevation, 6,000 feet or 1,700 meters or so, it gets very cold during the winter. And you have to pay people to shovel snow off the roof, basically. Otherwise, the amount of snow that falls on the top of the dome adds up to an enormous mass. But the problem is there's nothing there at the moment. The idea was we're going to start with a completely pristine mountain. We're not going to build where we already have an observatory. So the top of Palomar Mountain, this little snow-covered area up here, was not very accessible. There was a dirt track, not a tarmac road, a dirt track up to the top. And the idea is everything has to go up that dirt track. We're starting with nothing. So it's not just a question of building a telescope and an observatory dome. The entire observatory complex, all of the infrastructure, every piece of metal, every nut and bolt had to go up that road in order to start building the observatory. Okay, so we've decided that we've got $6 million in the bank. We decide that we're going to build a telescope that's 200 inches or 5 meters in diameter in terms of the mirror. How are we going to actually point that at the sky? Remember, the Earth rotates and hence the sky appears to move during the night. So you've got to move this telescope accurately if you want to, for instance, do long exposure photographs of some particular star cluster or nebula or galaxy or whatever. You're going to have to move this telescope very precisely. So the mounting is very important. For amateurs, you might decide, well, I've got this telescope the size of the size of a drain pipe or something, and I can mount it in various different ways. They're called German or fork mountings or English mountings. They're just different ways of doing it. Interestingly enough, these 3 different types, which are quite popular with amateurs, I think coincidentally, the 3 biggest telescopes that Hale actually made actually follow that series. The first one was on an equatorial or a German mount. The next one is on a fork mounting, though it looks rather odd because it's a very small fork. And more stable, if you hold it at both ends, then that you get this so-called yoke mounting. So there's the big 100-inch Hooker telescope in this yoke, as it were, which is being supported at the north end and the south end. This is somewhat important because it means if you have a big telescope like this, the big blue truss object here, you can't actually point it at the North Pole. You would like to be able to point it anywhere from your southern horizon, if you're in the northern hemisphere, the southern horizon all the way to the pole. And the pole is dictated by the angle of that yoke. In other words, the axis that we're looking at there points to the North Celestial Pole, the point immediately above the North Pole of the Earth. So this had a blind spot. It couldn't see a particular patch of sky. And Hale said, well, if we're going to build the world's biggest telescope and make it a 200-inch, we're going to make sure it doesn't suffer from the same problems as the Hooker telescope. The Hooker telescope had 2 main problems in terms of limitations on how it worked. One was the fact that this English yoke mount, this large girder structure you can see here, meant that the telescope could never point parallel with the yoke. It literally clangs and doesn't allow you to point in that direction. So that means a no-go area of the sky. And it seemed crazy to invest $6 million in a telescope that couldn't see a particular patch of sky. So they wanted to get around that problem. The other problem with the Hooker telescope, a 100-inch mirror was made of plate glass. And glass expands and contracts as the temperature changes. So if you're in an observatory dome and then the nighttime temperature is colder than you expected, the mirror would continue contracting as the mirror slowly cooled down to match the night temperature air, the air temperature. And it took hours to do that, depending on how many degrees difference between the observatory temperature and the nighttime temperature. Even if you predicted in advance what the night temperature was likely to be, it could still take hours for the mirror to slowly come to equilibrium temperature. And if it's expanding or contracting, then it's not the right shape to focus starlight. You have to wait till everything has settled. And if that took 6 hours, that means half your night was wasted waiting for things to come into equilibrium. Plate glass is not the best thing to make mirrors out of. It was cheap and useful back in the late 1800s, but Hale said, we can do better. Let's think about how we can do that. Firstly, how do we get around this no-go area around the pole? It was decided to make an iconic horseshoe mount. There's the horseshoe on the right-hand side, and there's the telescope that can point all the way to the south if it so wishes. And the difference with the old mounts is that if we want to, we can swing the telescope tube into the horseshoe, and the horseshoe is on the north side, so that if we want to, we can point the telescope directly at the North Pole. And as long as we wait to the right time of year, then all of the sky will be visible. We won't have any blind spots for this particular telescope. So that's why we ended up with this iconic horseshoe mount. The middle of the horseshoe allows the telescope to nestle into that position, and so you've got no blind spots. But what about the fact that plate glass is not a great way of making telescope mirrors? If we look sideways on, so this, remember the 100-inch Hooker telescope, it's 2.5 meters in diameter, half a meter or so thick, and we're looking into the side of the mirror. So there's the metal mirror on the top. The glass mirror is coated with metal to make it nice and reflective, but here we're just looking at how the glass was put together. And the glass, in this particular case, you have a large mold, you pour in your molten glass, and okay, not quite enough, so you get more molten glass, and you pour in, still not quite enough, you get a third, and so what you get is layers of glass, and also you get a whole load of air bubbles, and it looks absolutely horrible. And this contributes to the problem. So not only is plate glass very bad for expanding and contracting with different temperatures, if you've got air bubbles, they will expand and contract at different rates to the glass because air is not the same as glass. So again, the entire mirror would distort as it warmed up or cooled down overnight. And that's the last thing you want because you're trying to make a curved mirror that focuses light from a distant object. And you want that focusing to be perfect or as close to perfect as you can get. So a mirror that distorts at different temperatures is not quite useless, but it was certainly getting to the point where it was useless for many hours per night. So the idea of using plate glass doesn't work. What if you wanted to scale up a 100-inch mirror to a 200-inch mirror? Twice the diameter, 4 times the area. If it has to be twice as thick as well, you end up with a mirror which is 8 times as massive. The original Hooker mirror was 5 tons. Do you really want a mirror that weighs 40 tons and you're hoping is going to retain its figure when you're pointing it at different parts of the sky? Using plate glass would have exactly the same problems, except it would be even worse if you scaled it up. It would not simply take a few hours to come to equilibrium with the nighttime temperature of the air. It could take days, by which time the temperature would have changed again. Not only that, but if you're trying to make a mirror, you use molten glass and then you cool it down slowly until it becomes a solid. But how slowly do you have to cool molten glass to make sure that you don't end up cracking the mirror? Well, in the case of the Hooker telescope, 100-inch, you might have to cool it down slowly over many, many, many months from the original molten glass until you've reached room temperature. But it was calculated that if you simply scale up to a 200-inch mirror, it would take 10 years to cool from molten to room temperature. So you'd have to make the mirror 10 years in advance of the rest of the telescope. Not really applicable. So they changed and said, we're not going to use plate glass, we're going to use low expansion glass. Most of you know it under the trade name of Pyrex. Borosilicate. It basically, you can put it into the oven, you can take it out of the oven, you can put it under cold water. It doesn't crack because it doesn't expand and contract that much at different temperatures. Unlike plate glass, which if you did the same, heated it up and then put it under a cold tap, it would simply shatter. Borosilicate glass, or Pyrex, basically works much better. And this was a new technology at the time. And also, we want to avoid simply scaling it up and making it 8 times heavier. So it was decided to do things differently. Instead of having a mold which you pour glass into and fill up to make a pancake effectively, so imagine this is just a pancake side on, as it were. If you make a pancake of glass, you've got something that's roughly flat on the top and flat on the bottom. Once you've cooled it to room temperature, which could take a long time, you then grind it into a curve and coat that curve with metal. That then gives you a curved mirror which you can use to focus light. And if you get that curve right, it will focus light from stars or nebulae or galaxies from millions or billions of light years away. It's all about getting that curve precisely right. That's part of a problem. After cooling to room temperature, months is okay, many, many years is problematic. So they decided to do something rather revolutionary. They went to Corning Glass Works, the people who made Pyrex basically, and said, can we do this differently? And they said, yeah, there's an alternative. We have a mold, but we fill it with fire bricks. And then we pour the glass in as molten, and then it fills up by going around the bricks. When the mirror has cooled down, you take the bricks away, and you're left with a whole load of air gaps on the back of the mirror. In other words, you're left with a whole set of ribs. The front is exactly the same as before. You grind that down to the shape you want and you coat it in metal. But the back of the mirror is now ribbed, which means you've taken a lot of the glass away. It's just as strong as it was before, but now it's a lot lighter. So instead of having a 40-ton mirror, you've only got a 17, 18, 19-ton mirror. You still have to cool it slowly. It would still take about a year to cool down from molten glass to room temperature before you can actually start grinding it down. But 1 year is a damn sight better than 10 years. So what you end up with is a mirror which has got a ribbed back, which we'll see in just a second, because this is the mold where they filled it with fire bricks of particular shapes, and there's a big plug in the middle. You'll see why there's a big plug in the middle very shortly. But this is what the mold looks like. You heat the mold up, and then you pour your molten glass in, and the molten glass should flow around these fire bricks and give you a ribbed structure for the back of the mirror. I know you can't read all of what's going on here, but this is how the Corning Glass Works actually operated. There's a large mold here with what we've just seen, the fire bricks, and a large tank of liquid glass. In other words, about 50 tons of glass is molten in here, and then people with large ladles, looking all to the world like ice cream scoops, would scoop the glass out of the tank and then pour it into the mold. And this is them working. So they poke it into the glass tank. The load of people on the back end jump on the end of it because it's really heavy. They've picked up about 200 kilograms of glass. The ladle would melt if they didn't keep it cool, so they spray water on the ladle and then they're ready to take it away. Here it is from a different angle. The ladle goes into the tank, is turned, scoop up 200 kilograms of glass, pull it out. You've got a load of molten glass dripping off the bottom. Scrape away any excess. Get somebody with some water to spray water on the ladle to stop it from melting. And then you carry the ladle over to the mold. You put it into the open door of the furnace, and then you tip the ladle and pour. You can't really see the detail. You pour the glass into the mold. There's still a little bit of glass left in the ladle, so you tip it out into a wheelbarrow. And then you take the wheelbarrow back to the tank and recycle what you didn't use next time around. This has to be repeated hundreds of times to get 20 or 30 tons of glass from the tank into the mold. When you've done that, hopefully you've got a mold full, and then it's a question of slowly bringing it down from the molten glass temperature down to room temperature over the period of 10 or 11 months or thereabouts. There's a still showing you what's going on. There's the ladle. The weight is taken by an overhead rail system, and there's a whole load of expert engineers here who are supplying the muscle to make sure you can lift 200 kilograms, and the guy at the front is the one who decides, right, this is going in this door of the oven, and we're going to pour the molten glass into this bit of the mold. There's always a guy with a hat who is supervising, because that's their job. But here we see the workers who are tipping the ladle, and again, it's so bright in there you can't see what's going on, but they are trying to decide which bit of the mold we're going to pour this molten glass into to actually make our mirror. Notice that the oven in which this thing is sitting is made of bricks, and there's a whole load of heaters on the inside to keep it hot, hopefully for months at a time. Unfortunately, the first time this was tried by the Corning Glass Works in 1934, they had a little bit of a problem with the oven, and some of these bricks became dislodged. Also, some of the actual fire bricks in the mold themselves became loose, And because they're fire bricks, they're very light and they pop to the surface. And also any bricks that are falling in from the oven skabloosh onto the top, and you end up with a real mess. Even when you've cooled down to room temperature, by the time you've removed the bricks that had fallen in, you end up with gouges that are really deep. You can see how deep the mirror was, but those gouges are simply too deep. Even if you think about grinding it down to the curve you want to use as a telescope mirror, unfortunately, they are just too deep. So they learned from their mistakes, they rebuilt the oven, they made sure that the various fire bricks in the mold were not going to pop loose and come back up to the surface, and they tried a second time. In 1935, they got it right. And this is the result of, after a year, this is what you end up with. It's effectively flat on one side, hasn't been ground to shape yet. Flat on the far side, this is the back side of the mirror, and hopefully you can see the ribbed structure, which is the result of having lots of fire bricks around which the glass has flowed, and then when the fire bricks are removed, you end up with a very strong ribbed structure where most of the glass has been removed to give you a much lighter mirror. Here they are simply checking that there aren't any stresses in the glass to make sure it's been built the way they intended. That's simply a publicity photo to remind you how big the mirror is. The central aperture, which I'll come to shortly, why there's a hole in the middle of the mirror, is approximately 1 meter or so in diameter, and it gives you an idea of the scale. You can see the ribs are quite a few centimeters in thickness. For Corning, it was quite a coup d'etat because basically they said, we have made the biggest mirror in the world. This is the so-called eye. I don't know why, but they always seem to call these things eyes. Whether they were lenses or whether they were mirrors to be used in telescopes, they thought the public would understand better, if you call it an eye. And therefore they said, this is the eye that can see that many miles. Why did they choose that number? Because it was hoped that when this telescope was operational, it will be able to image galaxies 1 billion light years away. And 1 billion light years, when you convert it to miles, is that many miles. So they had all sorts of problems. It did work in 1935. They did correctly produce a Pyrex mirror, which was essentially perfect in terms of how it was constructed. They did have problems. They had problems with annealing ovens. They had a problem with a flood. They had a problem with an earthquake. A flood was about to hit the transformers that were providing electricity to keep the ovens hot, and they had to be very imaginative as to how they dealt with that, but they did deal with it, and the final mirror was declared as complete and perfect. Here it is coming to California. Here's the entire mirror. You can see it's sort of translucent when lit from behind. This mirror is about 20 tons and is on a strap and is being manhandled by people. So it's made in Corning Glassworks on the East Coast. It was then sent by rail over to the West Coast, making sure that the bridge clearance on the railway track was enough to get a 200-inch mirror through. Then, now you've got a glass slab, ribs on the back for strength, but effectively flat on the top. You want to grind it to the right shape, and it needs to be to the right shape to within a fraction, a tiny fraction of the wavelength of light. So it has to be accurate to basically a few tens of nanometers. Okay, it's a 5-meter diameter mirror, but you have to get it accurate to a few billionths of a meter when you grind it to the right shape. And that took 21 men, unfortunately, yes, men, 21 men. It took them 11 years to grind the mirror to the right shape. There's a reason it took a little bit longer than they planned. They thought it would take 5 years or so, and the reason why it took double that, I'll come to very shortly. So there's the people that were grinding it. It's not all done by hand, it's done by a machine. There's the mirror sitting on a large turntable, and a tool is rotating and moving over the surface of the mirror to try and grind it into the right shape. And a little bit of paste is being applied to allow them a little bit of sort of carborundum to get it to grind to the right shape. How do you know when you've got the right shape on that mirror? Well, generally, you grind a little bit and then you test it. And then you grind a little bit more and then you test it. How do you test it? Well, you shine light on it and see how that light is reflected. So you change the mirror. Notice that this is actually on a pivot, so the whole thing will float forward, pivot forward, and so the mirror becomes vertical. And then you can have a light at the end of the laboratory and see how that light is reflected off the mirror to tell whether or not that mirror is close to the right shape. What I find interesting about images like this from the 1930s is not the fact that somebody down here is using an electromagnet to try and pick up tiny particles of metal that would otherwise scratch the surface. What I find amazing is if you look at the people at the top, they seem to have pipes. I can't believe they actually allowed smoking in these optical laboratories. I think these people actually had empty pipes just because it was an affectation and they just felt naked unless they had a pipe in their mouth. So you put it into this position. You have to make very sure that you support the mirror carefully. This is 20 tons. How do you know it's not going to flex ever so slightly? You're trying to get the shape accurate to a tiny, tiny fraction of an inch, or if you wish, a billionth of a meter. So how do you know the mirror isn't flexing? It's a really big engineering problem to support that mirror such that it's the same shape regardless of which bit of the sky you're pointing at, whether it's directly up or whether it's horizontal. They did a test, it's called a knife edge test, where you send light next to a knife edge to see exactly what the shape of the mirror is. There's a test engineer there. You can see that's part of the knife edge test. And in principle, you grind it, test, grind it, test, grind it, test, and that's why it takes time. It's not simply a question of grind, switch it on, and when it's done, it's done. It is continuously refining and getting closer and closer and closer to the final figure that you actually want. Whilst the mirror was being produced in the California Institute of Technology optical workshop, they were building the observatory itself. So this is 1936, some piles went down, nice and easy. This is a slab of granite, so all you need to do is effectively bolt your superstructure to the granite and you're okay. So they started putting the observatory together. And then you have to think to yourself, well, we want to have a nice big dome to protect the telescope, but the dome has to rotate so that the telescope can look at various parts of sky. So you need to be able to make sure the dome rotates very, very smoothly. So you need to basically put the dome on wheels and then have a racetrack around the edge there. So this is the racetrack. The rails on the outer part are being ground down. The engineers said to Hale, well, what sort of tolerance do you want on these tracks? Said Hale, 1/1000th of an inch ought to be enough. You know, this is... And so the engineers were tasked with making sure that the rails on which the dome moves were so smooth. Bear in mind the dome itself weighs 1,000 tons. The idea is when the dome moves, the telescope shouldn't be aware of the fact the dome is moving. There should be no vibration, there should be no knocks. It should be effectively completely and utterly smooth, so that if you're taking an image of a distant galaxy and the dome needs to be rotated, not a problem. The dome rotates and it doesn't affect the pointing of the telescope. So once that track is done, you can start building the dome. This is now 1937, and by 1937 it starts to look like an observatory dome. You now have the sort of hemisphere on the top there. Things are all looking very good. This drawing, of which you saw the splash screen earlier, this is a drawing by a person called Russell Porter, who's an amazingly accomplished individual, a technical artist, if you want to think of it that way. His pencil and charcoal drawings were of such fantastic detail, some of the engineers building the telescope looked at his pencil drawings to say, have I got that in the right place? There's a blueprint here, but they often relied on drawings like this. Because they were cutaway drawings, they gave you a proper sense of what does this thing actually look like in 3 dimensions. And I'm going to use these pencil drawings just to give us an idea of what's going on. There's again the picture of a slice through the telescope. There's the mirror at the bottom, 200 inches in diameter. And yes, there are 3 people in this image. One of them is sitting up there in the so-called prime focus cage. This is one of the only telescopes in the world in which the astronomers are inside the telescope. because the telescope is that big that it's possible for an astronomer to sit inside. It's also a night assistant over there in the bottom right and another astronomer sitting down in the bottom. If we just dim that out slightly, I haven't bothered putting a curve on the mirror, but that's where the mirror sits. If we imagine that we were looking at a star, let's say, directly overhead, the light would hit the mirror and then come to a focus there. And that's where one possibility is the astronomer sits and puts his photographic plate, either eyeballs through an eyepiece or puts his photographic plate to take images of a distant object. Another possibility is you put a secondary mirror there, in which case the light hits the first mirror, then the second mirror, and then that's why there's a hole in the mirror. That's why there's a hole in the middle of the primary mirror, so that you can, if you wish, fold the light like that and put some of your instruments behind the main mirror. It's a standard way of designing telescopes. It's called a Cassegrain focus. But another rather clever possibility is there's also an option to put a third mirror in there, in which case the light hits the first mirror, then the second, then the third, and comes down here, where you have a guy here. Why would you bother? Well, A, it gives you a very long focal length, very high magnification. But the other advantage is this point doesn't move. No matter where the telescope is pointing in the sky, that focus is always there. So you can have very heavy, very cumbersome equipment, instrumentation, not necessarily cameras, but spectroscopes and other objects can be positioned down here, and you don't have to worry about lifting them or moving them because this point never actually moves. Let's have a look at how this thing was built. The tender was given to Westinghouse Corporation over in Pittsburgh. And this is some of the crew at Westinghouse who are standing in one of the rings that ultimately will hold the mirror in position. There's a few indications of the sort of size of the problem. Bear in mind the precision with which Hale wanted this telescope made. It has to be a very accurate telescope to make best use of a 5-meter mirror. It has to be able to point very accurately to a given object in the sky. So in a sense, it was said, it's like building a battleship, but to the precision of a Swiss watch. That's what these people were tasked with doing. Huge bits of steel work, but they had to be made very, very accurately. Here, some of the parts of the telescope truss have been put together. The idea was you put it all together, you bolt it all together, you make sure it looks right, and when you've got it right, you disassemble it and send it over to California to put on the top of Palomar Mountain. So this is a sort of topping out at the construction site. A number of people in the audience you probably don't recognize, but a dignitary on the right-hand side there was a certain Professor Einstein, because he was interested in saying, well, if you are going to be imaging these very distant galaxies, I have a certain theory which I've come up with that tells you about theory of relativity, general theory of relativity. I'm really interested. He's a theorist, not an experimentalist, not an observer, but he was still very interested in things like this to see whether or not they would prove that he was right. When asked, it's apocryphal, but when asked, why do you build telescopes like this? Somebody answered to Mrs. Einstein, well, we build large telescopes like this so we can see how the universe is put together on scales of billions of light years. To which Mrs. Einstein said, my husband can do that on the back of an envelope. Here's some of the stuff being put together. Part of the horseshoe. Remember the horseshoe at the end of the mount? Look how thick the steel is. 4.5 inches thick on the inside and on the outside. The plates were bent into shape with a 12,000-ton press forge. That is a huge amount of force required to basically bend 4.5-inch plates. And inside the horseshoe itself, it's ribbed again to give it structural strength and so not to flex. There's another publicity shot of some of the horseshoe being made. The horseshoe, when it was finished, was about 170 tons, made in 3 pieces, bolted together to make sure it all fits correctly, and then ultimately unbolted and sent over to California. But given this surface here is the surface on which the telescope rides, this is one of the bearing surfaces, it had to be phenomenally smooth. So there's a lug there in order to carry it around, but eventually that lug was removed. And then the outer surface was polished to within 1/1000th of an inch to the correct shape to allow it to do its job. The other end of the telescope mount, horseshoe at one end, this is the so-called south yoke. It looks a bit like a telephone receiver, especially in this particular view. This is the south end of the yoke. A couple of tubes are the yoke itself, which hold the telescope in the middle. But again, it gives you a nice idea of scale. Those are the tubes that will ultimately hold the telescope. There's the south yoke at this end, and not yet in place is the horseshoe, which would go on the right-hand side here. But all of this, when it's been shipped over to California, has to go up that grade. Remember the side of the mountain? Yep, everything has got to go up this dirt track, and that's what each of these individual pieces had to do. So they were made to a particular size to make sure that they could go up. So here, I think part of the horseshoe here, there's a truck pulling and there's a truck pushing. Notice the name of the company used. Hazard and Sons, yeah. As far as I know, nothing was lost. It was touch and go. Some of this is literally just lumps of concrete to give the truck traction to allow it to pull a few tons of steelwork up the hill. Once you get to the observatory, there's a hole in the observatory floor, and everything comes in at ground level and then comes up through this big square hatch in the observatory floor. So here the south yoke is coming through, the big telephone handset. We're now heading towards the late 30s. There's part of the horseshoe that's about to come up. There's part of the telescope that's already there. And then once you've got all the bits, you start putting it all back together again like a huge jigsaw. So they started putting it together. This is now 1939. You can get an idea of scale. There's a person hanging on. No bother with health and safety. No harnesses, no hard hats. Basically just people clambering all over the steelwork. Pretty much the same as building the Empire State Building, that sort of ethos. It's the same sort of age. It's the age of the Depression, where people were happy to get as much work as they could, and the idea of health and safety just wasn't a consideration. So here, at least this person's got a hat. Okay, it's a fedora, not a hard hat, but there we're looking at this cage. There's the cage in the middle of the telescope, the mirrors down the bottom end there. This is the cage in which the astronomer would sit in order to do their observations. So here they're just checking it out. And in order to make sure the telescope moved the way that it was intended, they basically said, let's just point the telescope south and make sure it works. So here's the horseshoe yoke, and the telescope itself is now coming down. It would never actually point at the southern horizon because San Diego's over there and it would be very murky. But just to make sure it did do what they thought it would do, they moved the telescope down. I guess this guy's an engineer. It looks like an engineer because he's got his sleeves rolled up. So they're just making sure that it does do what it ought to do. But how do you move such a large instrument? The telescope itself was something like 125 tons. The horseshoe mount, the horseshoe itself was 170 tons, remember. So the whole thing, the telescope and the yoke and the horseshoe that has to move to point to different parts of the sky, the whole assembly was about 500 tons. How are you going to move that precisely? Well, you have big gears. The gears themselves weighed a few tons, and you can see the gear, maybe you can see the individual teeth on the bottom. It's not so easy to see the teeth all the way round, but when you see the guy in the hat there popping up in the middle, it gives you, again, an idea of scale. How do you make sure you can grind a gear wheel to the accuracy you need to point with the accuracy you need? Astronomers are used to the idea of pointing with an accuracy which is quoted as arc seconds. If you think of a chunk of sky, think of 1 degree of sky, divide that degree up into 60 minutes, 60 arc minutes, and then take each arc minute and divide it again by 60 to get an arc second. So an arc second is 1/3600th of a degree. And the idea was this telescope could point to any part of the sky with an accuracy of an arc second. So it's a phenomenal thing to do with a small telescope. To do it with 500 tons is absolutely amazing. So how do you grind these teeth? Well, it takes you a while. A bit like grinding the mirror takes years, grinding the gears takes a while as well. Grinding the mirror takes a while, grinding these teeth, given that there are thousands of them. Well, you start by having a grinding wheel. There it is moving very slowly, and each of these is grinding the teeth. You can see the speed at which it's moving. You can see that it's going to take an awful long time to do the entire gear wheel. When you've got the grinding done, you start polishing, and this is now polishing with a polishing solution to try and get the teeth as smooth as possible so that when you drive it with a worm gear, it moves smoothly. How do you know when it's smooth enough? You get a man with a pipe to run his fingers over individual teeth, because that's apparently the best way of telling whether or not the teeth are smooth. And then your worm wheel engages and hopefully moves the entire telescope with the accuracy that you need. How big a motor do you need to move 500 tons across the sky? There it is, and you can get the scale. There you go. It only requires 1/12 of a horsepower to actually move this thing. With the motors decoupled, somebody tried setting up the telescope and balancing it, and then with the motors decoupled, they put a milk bottle on one side, and the telescope moved, showing you that it was extremely well engineered, and only small motors were required to actually move it around. I haven't really got time to tell you the wonderful work of Russell Porter. This is the gentleman who basically produced lots of fantastic drawings, technically accurate drawings, showing you what it would look like if it was transparent or cut away. I'm more than happy to send you high-resolution versions of these images. If anybody's interested, I can either make them available to Alan and Neil or take one of my cards and email me, but these are absolutely phenomenal when you look at them in detail. This is part of the drive mechanism. There's what's going on inside some of the yoke. That's how an astronomer might sit in the prime focus cage. There's the big mirror in the background, and there's the observer sitting in the prime focus cage. There's a different view of an observer. I don't know if astronomers always wore a suit to do their observing, but this is basically giving you an idea of how it's put together. And yes, an astronomer would sit there, and for long exposures, a photographic plate might be there, and they might make tiny tweaks to the position of the telescope to make sure it's pointing at the right galaxy for the rest of the night. Everything looked hunky-dory. Everything looked like it was on track. It was just months from being finished. The telescope tube was finished, the mount was complete, the mirror had been ground to within a fraction of a millionth of an inch of its life, and so everything was deemed to be almost ready to go. Except it's 1941. And that is what put the kibosh on the whole project. The USA was dragged into the Second World War. Bit late, but they got there in the end. And a lot of the mechanical workshops and the optical workshops were then repurposed for military purposes. It wasn't until 1945 they could resume the work that they had mothballed. Notice that the mirror, I hope you can see, is now somewhat dish-shaped. They've now ground it to approximately the right shape. It's quite a few centimeters lower in the middle than it is at the edges to give you the focusing that you need. In 1947, it was declared as it's as good as we'll get in the lab. There's a limit to how well you can test it in an artificial light source. What you really want is a star an infinite distance away to test it. So they put it in a crate, sent it up to the observatory. So there's the observatory floor before the mirror got put into the back end of the telescope. Gives you an idea of the size of the observatory, the fact that you could get 1,000 guests on the floor of the observatory. And at this point, it was dedicated and named. Up to this point, it was simply the 200-inch telescope. But in 1948, when it was essentially nearly complete, unfortunately, George Ellery Hale had died a few years earlier and never actually saw it completed. But that's why this telescope was at this point renamed from the 200-inch telescope to the Hale telescope, and that's been its name ever since. So the final business is to take the mirror. This is before it's got a metal coating. They are now trying to get that last perfect finish the last perfect figure of the right shape to focus light. So you put it in the back of a telescope, you point it at a star, you take an image, you either look or you take a photographic image, and you see if the star looks perfect. If it doesn't look perfect, you try and figure out, well, part of this mirror surface isn't quite right. It's a little bit too high there and a little bit too high there. Those white marks are where it is too high by a few millionths of an inch. And this expert comes along and tries to polish those down. Very, very carefully, because of course you don't want to take off too much. You polish them down. If you're not sure if you've done it right, you put it back into the telescope, you take a picture of a star. Is the star perfect? If not, you try and identify which bits of the mirror need polishing, you bring it out and you do a little bit more. The final polishing was probably no more than the master polisher here taking a little bit of jeweler's rouge on his thumb and that would take off maybe a millionth of an inch and hopefully get it close to a perfect shape. Now it's operating. There's an astronomer sitting in the prime focus cage. There's the drawing I showed earlier where that's a representation of the observer sitting up the top there. That's what it looks like in practice. Sitting there, the telescope is pointed almost horizontal, and then the astronomer climbs in, and then the telescope points at what you want. That's Edwin Hubble, the famous astronomer who decided that the universe appears to be a lot bigger than we first thought back in the 1920s. And I'm sure anybody, given that this is an open cage, it's not sealed in any way, everything is open to the night air, so I'm sure that they were very appreciative of the idea of the war surplus of flying suits that were electrically heated, allowing them to stay warm overnight. So here's an idea of what it might look like. Here's an astronomer. We've gone from a suit to a lumberjack jacket by the looks of it. So here he's going to put a photographic plate holder in position inside the prime focus cage. The plate holder goes in position and is locked down, and then the photographic plate is pushed into position. Whoa, 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 that's not it. Put it back. Yeah, okay, there, that one, that's it, yeah. So this is done in the dark, of course. The photographic plate is removed, put into position, and then the back of the, yeah, he's got it now. Yeah, then the back of the camera goes into position and is locked into place. Now we have a photographic setup that's okay, and we just have to do a few final checks. It's all secure by the looks of it, yep. Right, now let's make sure that we've got our sandwiches, because it's going to be a long session. Let's look at a star just off to the side of the photographic plate there. Make sure that we're looking at the star and the telescope is pointing in the right direction. If that is all looking good, then we're almost ready to go. Yeah, final double check of the sandwiches. Go on, go for it. Yeah, that's it, yeah. Okay, sandwiches are in place, we're ready to go, and we're pointing so we can open up the shutter and basically expose the photographic plate to the distant star or galaxy, whatever. And every once in a while, the astronomer would check that the star is on a set of crosshairs to make sure the telescope is pointing exactly where they want. And if there's any sign of that going slightly off position, they can just make tiny adjustments to the positioning of the telescope. And as of 1948, it was operational. A couple of years later, they took that picture, and that brings us full circle. That, I still think, is one of the most amazing images ever taken in astronomy. The fact that it's from the 1950s rather than from the Hubble Space Telescope or the James Webb Space Telescope, wonderful bits of engineering though they are, I'm still so impressed by what they could do in the 1940s and 1950s. Just to show you that it's still useful, it is still operating 77 years later, it's used as a test bed. It's no longer the biggest telescope in the world. That was overtaken some decades ago. The biggest telescope in the world has a mirror 10 meters in diameter, not 5, double the size, but only double the size. But the Hale telescope is used as a test bed for certain technologies. If they think something might be useful, they often put that technology into the Hale telescope to see how it works, and then decide whether or not it can be used in other telescopes around the world. So-called adaptive optics means changing your mirror shapes such that you get the best possible crisp image, even though you're looking through the Earth's atmosphere. So one of these images is taken by the Hale telescope with this so-called adaptive optics, and one of these images is taken by the Space Telescope, the Hubble Space Telescope, above the Earth's atmosphere, which isn't subject to the fact that the Earth's atmosphere is turbulent. But it's actually not the way around you think it is. That is a moon of Jupiter taken with the Hubble Space Telescope, and that is the same moon of Jupiter taken with the Hale telescope on Earth with this adaptive technology that allows you to get even sharper images. So if you take that technology and put it into other telescopes, like 10-meter telescopes around the world, you can get even better imaging. The telescope is in California. California is not the cleanest of states. Therefore, it needs to be cleaned every once in a while. So every once in a while, the mirror is dropped and then cleaned. So it looks very mucky there. So it's given a damn good wash. Yeah, it looks like they're scouring it. It's not quite that bad. They're giving it a good soapy wash to get the rubbish off. Then they put some mild acid on the surface, and the acid eats away the metal. Notice now that you can see the structure underneath. You can see those ribs. It's still a perfectly smooth surface, but we can see, because the glass is transparent, slight greeny color, we can see the structure underneath. So it's given a damn good clean, like this, and then it's put into an oven and recoated with metal, and then pushed back into the telescope, and hopefully good for another year or two of operation. It needs to be re-cleaned every 18 months or so because of the rather polluted atmosphere in that part of the world. So that effectively is the story of the Hale telescope, the 200-inch telescope, now 77 years old, the largest telescope in the world when I was born, the largest telescope in the world for my childhood, the largest telescope in the world for most of my adult life until it was overtaken a few decades ago. I visited it some decades ago, and I still think it's the most incredible piece of engineering. So I've been telling you about how Hale started this all by basically finding the money to do all of this. I told you a little bit about how they chose the site, how they made the mirror, how they made the telescope, and what it's doing now. Corning Museum of Glass had some useful information. Unfortunately, it's now moved, so those web pages have now moved somewhere else. But California Institute of Technology has got a lot of archives, and I'm indebted to the authors of these 4 books because they give a lot of information about how the early decisions were made, the designs, the construction, etc. So the fact that after 77 years, this telescope is still producing some amazing results is testament to the scientists and the technicians who designed and built and tested this telescope. But as much more than anything else, it is testament to the man that had the vision to pull it all together, George Ellery Hale. Thank you all very much.